Hi everybody, this is Professor Bell. I'm going to try making a video. I got a video camera from the college a few days ago and I'm going to see how this goes. What I'm going to go over now is an old test over chapter 7, 8, and 9. So if you want to look at a few more examples before you take the test, I know the test goes through tomorrow night and some of you have already taken it, but I just got this thing set up. Now it's on a bendable arm, so it's wobbly, so if it looks like it's wiggling, I can't do anything about that because the webcam is very small and I had to clip it into this arm. Tomorrow I'm going to try to record some notes for chapter 10 and chapter 11, not all at the same time, and post those. Now that I have the camera, I'm hoping to do a little more posting of videos. I did post the completed notes for chapter 7, 8, and 9. So if you look over those, there was a more thorough explanation in addition to the interactive assignments that are in the My Math Lab course. And this is, like I said, an old test, so I'm just going to go through these questions. I have the chapter marked beside each question so you can see what chapter this would come from. In this first question, it says, suppose that the talk time on the Apple iPhone is approximately normally distributed with a mean of 7 hours and a standard deviation of 0.8 hours. What proportion of the time will a fully charged iPhone last at least 6 hours? So we have the mean and the standard deviation from the problem, and we want the probability that x, the talk time, is greater than or equal to 6. So for this, we'll use the normal CDF in our calculator, and we'll put in 6 as the lower limit, and the upper limit is positive infinity, so we'll use 1e99, the mean and the standard deviation from the problem. And remember that our normal CDF is under distributions, so right here. So it's a second function, second distribution, and it's number 2. And we put in the lower limit of 6 and the upper limit, and then here we have the mean, which is 7, and we have the standard deviation, which is 0.8, and we go ahead and calculate that. And when we round off to 4 places, because this is a probability or a proportion, those are 4 places, and we have 0.8944. So that's the proportion of iPhones that we would expect to last 6 hours or more of talk time. What is the probability that a fully charged iPhone will last less than 5 hours? Well, in this one we need to do the same distribution, normal CDF, which is under distributions, number 2, and we want the probability that x is less than or equal to 5, so we put in negative infinity as our lower limit. Our upper limit will be 5, and then the same mean and standard deviation as the previous problem because they have the same information. And what we will get there is 0.0062 when we round off to 4 places. What talk time would represent the cutoff for the top 5% of talk times? And I've drawn the distribution here, and the top 5% is shaded in up here approximately. And this is an inverse norm question. And remember that for most of us, the inverse norm, we have to use the area to the left of the value we're looking for, even if we're given the area to the right. Some of you have the newest model of calculator, and it allows you to choose left or right, and then you can put in the area to the right. If that's where it is, you could put this in and put in 0.05. My calculator isn't that new, and so I have to put in the area to the left. And the area to the left of this is 1 minus 0.05. You can even just put it in like this. You don't have to subtract it and then put that number in. It's a calculator. If you put in 1 minus 0.05 for that, it will know what you're talking about. So we use the inverse norm, which is number 3 under distributions. So second distribution, 3. The area is 1 minus 0.05. The mean is 7. The standard deviation is 0.8. And so the cutoff, when we round to 2 decimal places, since this isn't a probability but it's an actual value from our distribution, it would be 8.32 when we round off. So 8.32 hours would be the cutoff for the top 5% of talk time minutes in that iPhone distribution. Would it be unusual for the phone to last more than 9 hours, and why? And in this one, I won't go through it in the calculator, but I used the normal CDF. I was looking for the probability that x is greater than or equal to 9, so I started with 9. Then the upper limit is infinity, so 1e99, the 7 and the 0.8 that we've been using in this problem. And we get 0.0062 as the probability that the talk time would last more than 9 hours. And that would be unusual because remember, all along we've sort of used our rule of thumb has been that unusual is anything that is less than 0.05, and 0.0062 is definitely a lot smaller than 0.05. So it would be unusual for a phone to last that long in talk time. All right, number 2, also from Chapter 7, the waist circumference of males from 20 to 29 years old is approximately normally distributed with a mean of 92.5 centimeters and standard deviation of 13.7 centimeters. So I've got that written out here for us to refer to. What is the probability that a randomly selected 20 to 29-year-old male has a waist circumference between 80 and 100 centimeters? So we've got a lower limit and an upper limit that neither one is infinity. We would put this in normal CDF, and so we're here. Our lower limit is going to be 80, and our upper limit is going to be 100, and our mean is 92.5, and our standard deviation is 13.7. So we get 0.5272 when we round off to 4 decimal places. So that is the probability that we would have a 20 to 29-year-old male with a waist circumference somewhere in here in centimeters. All right. On the next page, determine the waist circumference that is the 10th percentile. Now remember, the 10th percentile is the value that cuts off the bottom 10%. So I've got the picture drawn here. This is the same mean and standard deviation because we're still working in the same problem we just were. So the inverse norm is what would give us that value, and I put in the left area, so it's 0.10. My mean and my standard deviation, that's all I need for the inverse norm. So distributions, this is 3. The area is 0.10, 92.5, 13.7, and I get 74.94 when I round to 2 decimal places. Again, this is a data value, so I don't have to round to as many decimal places. And so 74.94 centimeters is the cutoff for the lowest 10% of measurements. Number 3 is also from Chapter 7. We've been asked to find the z-score such that the area under the standard normal curve to the left of that score is 0.53. Now remember, the mean cuts this distribution in half. So to the left of this is 0.5. So if the area is 0.53, we should expect it to be a little to the right of the mean. And for the standard normal distribution, the z-score distribution, the mean is 0 and the standard deviation is 1. So we would put in inverse norm, and the area is 0.53. The mean is 0 and the standard deviation is 1. And we get 0.0753. And because this is a z-score, we wouldn't round it to 4 places. We typically would round that to 2 places. So 0.08 is probably where they would ask you to. Remember, always in the question, pay attention to where they've asked you to round to, because that's what it's programmed to count correct. If I was hand grading these, I can be a little bit more lenient, but MyMathLab is programmed to expect you to follow their directions. This is asking for what percentile. Well, if 53% of the values are below that, that is the 53rd percentile, because remember, percentiles tell us the percent that is below that value. Ask me to sketch and label the standard normal curve, shade the area, and mark the z-score. I did that here. Up here I had the sketch, but I hadn't marked the z-score. It was still a question mark then. But here, now that we found it, 0.0753, or if we rounded off 0.08, here is the area, 0.53, and that is the sketch. Number 4 is also from Chapter 7. Assume that the mean systolic blood pressure of normal adults is 120 millimeters of mercury, and the standard deviation is 5.6. Assume the variable is normally distributed. So we have the mean of 120, the standard deviation of 5.6. This is for individuals. If an individual is selected, find the probability that the individual's pressure will be between 120 and 121.8 millimeters of mercury. So this is a normal CDF. This is an individual, so we use the mean and the standard deviation exactly as they're given. And we put in, the lower is 120. The upper is 121.8. The mean is 120. And the standard deviation is 5.6. So we get 0.126 blah, blah, blah. And if we round to 4 decimal places, this is a 5. So that goes up to a 1, and we get 0.1261. Moving on to the second part of this, this comes from Chapter 8, because remember in Chapter 8, we talked about random samples when we have a sample from a population, and the central limit theorem talked about the distribution of the sample means. So this is the same set of data we used before, the 120 mean and the 5.6 standard deviation for the entire population. But for samples, we change the standard deviation. We divide the population standard deviation by the square root of the sample size, because the sample means, when you take them in groups, not just individuals, the sample mean has a different standard deviation. The mean doesn't change, but the averages from all those groups has a different standard deviation, and this is the formula for calculating that. So when we are talking about a random sample, then we use the mean here and then the standard deviation we get from here. And you can put it in the calculator exactly like this. You don't have to calculate it and round it off first. You can just put it in like that. So if we have a random sample of 32 adults, according to the central limit theorem, what are the mean and the standard deviation? Now this one, it does ask, if you put it in like this, MyMathLab might not like it. They probably want you to estimate it like this, but you can put it in the calculator like this in terms of finding something from the distribution. So the mean is still 120, but the standard deviation now is 5.6 divided by the square root of 32, which is 0.9899. So it's a lot smaller. The standard deviation is a lot smaller when you're talking about the distribution of the sample means as opposed to the distribution of the individual values. This one is also from Chapter 8. If a sample of 32 adults is randomly selected, find the probability that the mean pressure will be between 120 and 121.8 milligrams of mercury. So this is the same type of question we answered before, but before we were asked about a single individual, the probability that their blood pressure was in this range. And now we're being asked, if we sample 32 adults, what is the probability that the average of that group of 32 people, their average blood pressure will be between these two numbers? And so we figure it exactly the same way, except for that standard deviation. So we have second distribution, 2. And now, instead of the 5.6, we have the 120 for our lower limit, the 121.8 for our upper limit, 120 for our mean, and now our standard deviation. I'm going to go down here and I'm actually just going to adjust it by putting in divided by the square root of 32, because like I said, it's a calculator and it'll do this for me. And then when I go to my answer, I get 0.465, and then this rounds to a 5 because there's an 8 next to it. So 0.4655. So that is the probability that the average from a group of 32 people out of this population, that the average blood pressure of those 32 people will be in this range. Number 7 and 8 are the same kind of question. 7 comes, or number 5A and 5B, part A comes from chapter 7 because it's an individual, one randomly selected student, and part B comes from chapter 8 because it's a group of 50 students. After this one, I'm going to stop this recording and then make a different recording for the other, the rest of it, just for length purposes. The salaries for full-time PhD students are distributed with an average of $12,837 per year and a standard deviation of $1,500. So this, for an individual, we would use these numbers. So for number 7, we'll use both of these. For number 8, we'll use this as the mean, but remember we have to adjust the standard deviation when we are looking at the average for a group that is randomly selected out of the population and not just one individual from the population. But while we're still talking about the individual, this is a randomly selected student. So we use the normal CDF. We put in 15,000 as our lower limit, because we're talking about the probability that they will make more than that. So the bottom limit is 15,000. And then the upper limit is infinity. I don't think any graduate student is making infinity dollars a month, but that's it, there's no upper limit given. So we have 1E99. And then the mean is 12,837. And the standard deviation is 1,500. And we get 0.0747 when we round off to 4 places. So that's for one person, one graduate student from this population. But what about if there was a randomly selected group of 50 graduate students? What is the probability that their average, the average for the whole group of 50, is more than 15,000? So we do the same thing, but now we have to make the standard deviation equal to the old standard deviation, the $1,500, divided by the square root of the sample size, which is 50. So I'm going to go back to that. Everything else is the same. The lower limit is 15,000. The upper limit is positive infinity. The mean is the same. The mean doesn't change when you take a sample. It's just the standard deviation that changes. And the standard deviation is now going to be 1,500 divided by the square root of 50. And we get an extremely small number, 1.049 times 10 to the negative 24th. So it's like if I move this decimal point to the other side of the 1, I would have to put 23 zeros before I would end up putting the decimal point down. So that is so small that for all practical purposes, that probability is 0. So there's just almost virtually no possibility. The probability is basically 0 that a group of 50 graduate students from that population would have an average, the average of all 50 of them would be more than $15,000 a year from the time that this data was collected. All right, I'm going to stop right here, and then I'm going to start another recording for the rest of the questions. It's another several pages, so it's about the same length.